In the domain of critical infrastructure protection and maritime port defense, time is the ultimate vulnerability. For the past decade, commercial drone operations have been severely limited by the chemical boundaries of lithium-polymer batteries. A standard industrial quadcopter can stay airborne for roughly 40 minutes before it is forced to descend, swap batteries, and recalibrate its sensors. During those minutes of battery management on the ground, the security perimeter is broken. The sky is empty. Against asymmetrical threats, moving maritime targets, and stealth surface vessels, 40 minutes of flight time is completely useless. This operational bottleneck has forced aerospace engineers to reimagine the foundational physics of drone endurance. The solution is a radical departure from independent flight. It is called Power-over-Tether technology. By physically anchoring the unmanned platform to a ground power station via an ultra-thin, high-tensile micro-tether, engineers have extended drone endurance from 40 minutes to multiple days of continuous flight. Operating at heights up to 150 meters, these airborne sentinels provide uninterrupted, 24/7 surveillance, acting as permanent virtual towers in the sky. They carry heavy optical and thermal payloads, radar systems, and communications relays without ever needing to land. But replacing a localized battery with a 150-meter hanging copper line introduces an extraordinary physics paradox. How do you send thousands of watts of electrical energy up a cable that must remain thin enough and light enough for a drone to lift? To find out, we must look inside the complex mechanics of high-voltage micro-tether architecture. To deliver enough electrical power to run 4 high-power brushless motors and heavy stabilization gimbals, a drone requires roughly 3 to 5 kilowatts of continuous energy. If we try to transmit this power using standard commercial voltages, such as 24 or 48 volts direct current, we run directly into the brutal reality of the Joule-Lenz Law. This physical law states that power loss in an electrical conductor is equal to the current squared, multiplied by the electrical resistance of the wire. High current creates immense thermal energy. To prevent a 48-volt cable from overheating and melting under a 5-kilowatt load, the copper conductors would need to be thick, heavy, and dense. A 100-meter spool of such a cable would weigh more than 20 kilograms. The drone would be physically crushed by the weight of its own power cord. To break this paradox, aerospace engineers do exactly what electrical grid companies do. They boost the voltage and drop the current. Modern micro-tether systems operate at extreme voltage levels, typically between 400 and 800 volts direct current. By increasing the voltage vector by a factor of 16, the required current drops exponentially. This drop in current allows the copper conductors to be engineered with microscopic diameters, often thinner than a millimeter. The entire core is reinforced with a central high-tensile aramid yarn sleeve to handle mechanical tension, and wrapped in a specialized aerospace-grade fluoropolymer insulation jacket. The result is a high-voltage micro-tether that weighs less than 1.5 kilograms per 100 meters. The drone can lift it effortlessly, leaving 90% of its payload capacity free for advanced security sensors. Sending 800 volts up the micro-tether solves the weight problem, but it introduces a severe hardware challenge on board the aircraft. Standard brushless drone motors and electronic speed controllers cannot accept 800 volts. They operate on low-voltage direct current, typically between 24 and 50 volts. This means the drone must carry its own miniature substation. An onboard high-efficiency step-down conversion system, known as a DC-to-DC buck converter. This power module must accept the high-voltage, low-current stream from the tether and transform it into a stable, low-voltage, high-current power rail for the propulsion system. From a thermal management perspective, this conversion process is incredibly intense. Even with a high power delivery efficiency rating of 96%, converting 4 kilowatts of energy means that 4% of that power is lost entirely as waste heat. That equals 160 watts of pure thermal energy generated continuously inside a tightly packed, sealed carbon fiber chassis. Without active cooling, the silicon transistors inside the buck converter would reach their critical thermal limit and undergo immediate semiconductor breakdown in less than 90 seconds. To prevent catastrophic thermal shutdown, the mechanical structure of the drone is engineered around aerodynamic heat dissipation. The buck converter is hard-mounted to an anodized aluminum heatsink that forms the lower floor of the drone's chassis. The cooling fins of this heatsink are positioned directly within the high-velocity downward airflow generated by the spinning propellers. This constant aerodynamic prop wash forces hundreds of liters of cool air through the cooling channels every minute, maintaining the internal electronics at a stable operational equilibrium even during intense midsummer port deployments. An industrial tethered drone system is not just an aircraft. It is a highly synchronized dual hardware ecosystem consisting of the airborne platform and the intelligent ground winch station. Managing 150 meters of high-voltage cable in variable weather conditions requires an active, automated mechanical response. A cable hanging loose in the sky is a deadly hazard. If the wind drops suddenly and the tether develops slack, the wire can loop upward, leading to immediate propeller entanglement and mechanical destruction. To eliminate this operational risk, the ground station utilizes a smart winch system powered by an independent high-torque servo motor and a continuous tension tracking loop. The ground firmware monitors the physical pulling force exerted on the micro-tether at a sampling rate of 200 Hz. It is programmed to maintain a perfectly constant tension vector, typically around 15 newtons of force. When a strong ocean wind hits the drone and pushes it sideways, the smart winch instantly detects the spike in mechanical tension and smoothly pays out the necessary length of cable to prevent pulling the drone out of its sky position. Conversely, when the drone descends or the wind stops, the winch retrieves the slack in milliseconds. If a catastrophic environmental event occurs, such as a lightning strike or a physical severance of the micro-tether by a passing vessel, the onboard avionics execute an immediate hardware-level override. The flight computer instantly detaches the dead tether interface, switches to the emergency onboard lithium backup battery, initiates an encrypted radio frequency link, and executes a controlled autonomous landing inside a pre-designated safe zone. This is the peak of modern automated infrastructure defense. By mastering the strict physical interplay between high-voltage power transmission, advanced material science, and real-time mechanical tension management, systems engineers have successfully rewritten the rules of aerial endurance, securing the industrial frontiers of the modern world. Thank you for watching this technical breakdown on BlackBox UAV. Stay analytical, verify your telemetry parameters, and we will see you inside the next BlackBox session.